All right, class, so this is a practice problem where we're going to be talking about a diprotic acid, meaning an acid that can give off more than one equivalent of H+. And so my oxalic acid, H2C2O4, that's going to be my weak diprotic acid. I've been given a Ka1 and a Ka2. Ka1 is going to represent the first dissociation, so getting rid of that first equivalent, and then Ka2 is going to be the second equivalent. And we should always expect our Ka2s to be much smaller than our Ka1s. Our Ka2 is going to be much smaller because it's going to be harder to get rid of that second equivalent of H+ from our species. And this question is asking to calculate the concentrations of all the species present at equilibrium if we start with a 0.1 molar solution. I'll also solve for the pH in this case because it's just something we can add in and sort of throw in. So I've got some notes here to sort of help you out in terms of solving this problem, but I'm just going to walk through it. The first thing that I'm going to do is going to sort of write out my Ka1 expression. So Ka1 is going to be the dissociation of H2C2O4 into H+, and then the conjugate base, HC2O4 minus. This is going to be my Ka1, and I've got a value of that of 6.5 times 10 to the minus 2. My initial concentration of my acid here, my weak acid, is going to be 0.10 molar, and then 0 or essentially 0 for H+, and for my conjugate base. My change line is going to be minus x, and plus x. And then at equilibrium, I'll end up with 0.10 minus x, and x. Now, the next thing I'm going to do is solve this using the quadratic formula. So 6.5 times 10 to the minus 2 is going to equal x times x, so the products over the reactants, 0.10 minus x. And I'm going to solve for x. And like I said, in this case, you actually need to use the quadratic formula. You need to sort of group things together. I'm not going to show that on this video, but suffice it to say, you'll need to use the quadratic formula. The reason for that is because this Ka value here, it's small, but it's not that small. This minus x term here is not negligible. It will actually change this 0.1. So we need to solve exactly here. So if you solve the quadratic formula, you're going to end up with a x value of 0.0544 molar. And you can see that that will affect this 0.1, right? So if we were just doing our check, we would see pretty easily, oh yeah, that is going to play a role. So this x value here, that's going to equal the concentration of H+, and that's going to equal the concentration of HC2O4 minus. We could also solve for the concentration of our starting material, H2C2O4 is going to equal 0.1 minus x, so just plugging in that x value that I solved for here. So I could solve for that. That's going to equal 0.0456 molar. Now, this HC2O4, this is going to be our diprotic acid, right? It's going to continue to give off H+ equivalents. So for the next part of this, what we're going to want to do is we're going to want to consider that Ka2 reaction. So I'm going to take that HC2O4 that I produced in step 1, and I'm going to continue that dissociation process to form C2O4 2 minus, and I will have a Ka2 that's associated with this. This is my second equivalent of H+, so I'll be using the Ka2. And my value for that is 6.1 times 10 to the minus 5th. Now my initial concentrations here for HC2O4, that's going to come from what I sort of produced in the first step. So that's going to equal that x value, 0.0544. And then for H+, it's also going to be the same, 0.0544. Right? And that's because I am producing H+ as well. So my initial concentrations, or my final concentrations here, those are going to become my initial concentrations in the second step. I don't have any C2O4 2 minus yet, so that will still be 0. Let's move this up. So then my change line, minus x plus x plus x. I know that I need to still shift to the right because I have a 0 here. And then at equilibrium, 0.0544 minus x, 0.0544 plus x, and then x for C2O4 2 minus. Again, now I can set up my equilibrium constant expression times 10 to the minus 5th is going to equal 0.0, to make sure you guys can see it, 544 plus x times x over 0.0544 minus x. Now in this case, we've got a very small Ka value. And so this minus x term, it's going to end up being negligible, and we can also double check that in just a minute. But this minus x term, as we've seen in previous Ka problems, we can say that that's going to be negligible, and we can sort of cross that out, and we'll simplify solving this problem. But it stands to reason that if this minus x term is negligible, then if I do the same thing and I add x, well, that should also be negligible, right? If you subtract it and it doesn't change it, well, if you add it, it also shouldn't change it as well. So I can get rid of both of those, make that little assumption. Now, these terms will both cancel out, and we can easily see that the x value is going to just equal the value of Ka2. And this is going to be a general thing that we're going to run into. So this x value for this Ka2 is going to equal, in this case, right, because we've got this 0.0544 plus x, 0.0544 minus x, since these started with the same initial concentrations, it simplifies really easy for us to solve for this x value. We can solve for the concentration of C2O42 minus now. That's just going to equal the x value. Now, for our concentration of H plus and our concentration of HC2O4 minus, since this x value is so small, these equilibrium concentrations, they're actually just going to end up being the same as our initial concentrations. It's just going to dissociate just a tiny, tiny bit, and that tiny, tiny bit is really negligible as compared to my initial concentration. So really, in step 1, we're solving for the equilibrium concentrations of all three of these things, and then in step 2, we're just adding in this extra piece right here. So if I wanted to find the pH, the last thing I said I was going to do in this problem, that equals the minus log of the concentration of H plus, right? And the concentration of H plus that I'm going to want to use is this concentration of H plus at equilibrium. Well, since this plus x term is negligible, really the pH of this is just going to be based off of what we did in step 1. So I can just use this concentration here for H plus to solve for the pH, and that's going to be a general case. The first equilibrium is always going to determine the pH. And then the second equilibrium, the second steps of these diprotic or triprotic systems, they're just going to be for solving for the extra, ion or whatever else is formed in the solution. So in this case, I can solve for the pH, and that's going to end up being 1.26. So that would be my final pH. My concentrations, I'll put boxes around all of the different things that we're solving for here. This is the remaining concentration of my starting material, and then my H plus concentration, and my HC2O4 minus concentration. Really, it's probably more correct to use these expressions, right? But like we said, this minus x and plus x is going to be negligible, so it's really the same as what we have up here. All right, hope that helps. See you guys later.